It is possible to have a square D panel that is fed by a main bus to a 70-amp breaker, which in turn feeds the buses by number 6 wire. This configuration is typically seen in older panels. This specific setup is generally not recommended for new installations because modern panel designs often prioritize more direct and robust connections to the main service. The main breaker in this type of configuration serves as the main disconnect for the entire panel. It's the point where you can shut off all power to the circuit served by that panel. It also provides overcurrent protection for the entire panel. This means that it is designed to trip or switch off if the total current flowing through the panel exceeds its rated amperage, which in this case is 70 amps. The number 6 wire that feeds the buses is sized to handle the maximum current that can be drawn by the panel. The National Electrical Code, or NEC, specifies ampacity ratings for different wire gauges based on their material and insulation type. For copper wire with a common insulation type like THHN, number 6 wire typically has an ampacity of around 55 amps in a 60°C environment, 65 amps in a 75°C environment, or 75 amps in a 90°C environment. However, the specific ampacity must be verified based on the actual wire type and installation conditions to ensure compliance with the NEC. If the number 6 wire is feeding a 70-amp breaker, it's crucial to verify that the wire's ampacity is adequate for the breaker size and the anticipated load. If the ampacity is lower than the breaker rating, it could create a fire hazard under overload conditions. It is important to note that this configuration can be potentially dangerous if the main breaker is not properly sized or if the wiring is not in good condition. If the main breaker is too small, meaning its amperage rating is too low, it may not be able to handle the maximum current that can be drawn by the panel when all or many of the branch circuits are in use. This can lead to nuisance tripping of the breaker, constantly interrupting power. More seriously, if the panel draws significantly more current than the breaker's rating, it could overload the breaker and potentially cause it to fail. A failed breaker may not trip in an overcurrent situation, which can lead to overheating of the wires and potentially a fire. For this reason, it is extremely important to have the panel thoroughly inspected by a qualified and licensed electrician. The electrician can assess the overall condition of the panel, verify that the main breaker is properly sized for the expected load, and check that all wiring connections are tight and secure. During an inspection, the electrician will likely perform several checks. Firstly, a visual inspection of the panel. The electrician will look for any signs of damage, such as rust, corrosion, or overheating. They will also check that all the breakers are properly labeled and in good working condition. Secondly, load calculation. The electrician will perform a load calculation to determine the total current that the panel is expected to draw under normal operating conditions. This calculation takes into account the amperage ratings of all the branch circuits in the panel and any other loads that are connected to the panel. Thirdly, breaker sizing verification. Based on the load calculation, the electrician will verify that the main breaker is properly sized. The NEC provides guidelines for sizing breakers based on the expected load. Fourthly, wiring inspection. The electrician will inspect the wiring in the panel to ensure that it is in good condition and properly sized for the breakers that it serves. They will also check that all wiring connections are tight and secure. Fifthly, testing. The electrician may use various testing instruments to check the voltage and current levels in the panel. They may also use a thermal imaging camera to identify any hotspots, which could indicate loose connections or overloaded circuits. If the inspection reveals any problems, the electrician can recommend the necessary repairs or upgrades. This might include replacing the main breaker with a larger one, replacing damaged wiring, or adding additional circuits to distribute the load more evenly. Regarding the NEC, several articles and sections might be relevant to this type of panel configuration. NEC Article 220. 87 deals with load calculations for existing installations. This article provides guidance on how to determine the existing electrical load of a building or structure. NEC Article 230 covers services. This article covers the requirements for the electrical service entrance to a building, including the surface conductors, overcurrent protection, and grounding. NEC Article 240 deals with overcurrent protection. This article covers the requirements for overcurrent protection devices such as circuit breakers and fuses, including their selection, installation, and protection of conductors. NEC Article 310.15 addresses conductor ampacity. This article provides tables and guidelines for determining the allowable ampacity of conductors based on their size, insulation type, and installation conditions. It's important to consult the specific edition of the NEC that is in effect in your jurisdiction for the most up-to-date requirements. Here are some additional considerations regarding a square D panel fed by a main bus to a 70 amp breaker with number 6 wire feeding the buses. Firstly, the age of the panel. Older panels may not meet current safety standards. Wiring insulation can degrade over time, and components can become worn or corroded. If the panel is very old, it may be wise to consider replacing it with a new one that meets current codes. Secondly, the load on the panel. If the panel is heavily loaded, it may be necessary to upgrade the main breaker and wiring to handle the increased load. This is especially important if you are planning to add any new appliances or equipment that will draw a significant amount of current. Thirdly, the condition of the wiring. If the wiring in the panel is damaged or deteriorated, it should be replaced. Damaged wiring can create a fire hazard. Fourthly, proper labeling. All circuits in the panel should be clearly labeled so that you can easily identify which breaker controls which circuit. This can be helpful in an emergency. Fifthly, surge protection. Consider installing a surge protector to protect your electronic equipment from power surges. Surge protectors can be installed at the main panel or at individual outlets. Sixthly, arc fault circuit interrupters, or SIs. SIs are a type of circuit breaker that is designed to protect against arc faults, which are a common cause of electrical fires. SIs are now required in many new construction and renovation projects. Seventhly, ground fault circuit interrupters, or GFCIs. GFCIs are designed to protect against ground faults, which can occur when electricity leaks from a circuit to ground. GFCIs are required in areas where there is a risk of water exposure, such as bathrooms, kitchens, and outdoor outlets. Eighthly, professional inspection. Regular inspections by a qualified electrician are essential to ensure the continued safe operation of your electrical panel. It is good practice to have your panel inspected at least every 3 to 5 years, or more frequently if you have any concerns. When dealing with electrical systems, it is always best to err on the side of caution. If you are not comfortable working with electricity, it is best to hire a qualified electrician to do the work. Incorrect wiring or improper breaker sizing can lead to serious safety hazards. Here are some potential issues with the described square D panel configuration and how to address them. Firstly, inadequate wire ampacity. If the number 6 wire does not have sufficient ampacity for the 70 amp breaker, it is a fire hazard. Solution: replace the number 6 wire with a wire gauge that is rated for 70 amps, such as number 4 copper wire, ensuring compliance with NEC Table 310.15. Secondly, breaker misapplication. The 70 amp breaker may not be appropriately sized for the loads served by the panel. Solution: perform a load calculation to determine the actual load on the panel. Replace the 70 amp breaker with one that is properly sized for the calculated load, following NEC guidelines. Thirdly, loose connections. Loose connections can cause arcing, overheating, and potential fire hazards. Solution: inspect all connections in the panel and tighten any loose connections. Consider using a torque screwdriver to ensure proper torque on the connections. Fourthly, corrosion. Corrosion can increase resistance, leading to overheating and potential failure of components. Solution: clean any corroded components and apply a corrosion inhibitor. Replace any severely corroded components. Fifthly, damaged insulation. Damaged insulation can create a shock hazard or short circuit. Solution: replace any wires with damaged insulation. Ensure that all wiring is properly protected from physical damage. Sixthly, improper grounding. Improper grounding can create a shock hazard. Solution: verify that the panel is properly grounded according to NEC requirements. Check the grounding electrode, conductor and connections for corrosion or damage. Seventhly, overcrowding. Overcrowding of wires in the panel can make it difficult to work on and can increase the risk of shorts. Solution: organize the wiring in the panel to ensure that it is not overcrowded. Use wire ties or other means to keep the wiring neat and orderly. Eighthly, lack of labeling. Lack of clear labeling can make it difficult to identify circuits and can increase the risk of errors when working on the panel. Solution: label all circuits clearly and accurately. Use a permanent marker or label maker to create durable labels. Ninthly, outdated components. Older panels may contain outdated components that do not meet current safety standards. Solution: consider upgrading the panel to a newer model with modern safety features, such as arc fault circuit interrupters, RF size, and ground fault circuit interrupters, or GFCIs. Tenthly, environmental factors. Moisture, dust, and other environmental factors can damage the panel and its components. Solution: protect the panel from moisture and dust. Consider installing a panel enclosure if the panel is located in a harsh environment. When evaluating the safety and suitability of this type of panel configuration, it is essential to consider a range of factors and not solely focus on the presence of a 70-amp breaker fed by number 6 wire. Firstly, the overall condition of the panel. A visual inspection of the panel is crucial. Look for any signs of rust, corrosion, water damage, or physical damage to the enclosure or components. Check for any evidence of overheating, such as discoloration or melting of wires or components. Secondly, the integrity of the wiring. Carefully examine the wiring for any signs of damage, such as cuts, abrasions, or brittle insulation. Ensure that all connections are tight and secure, and that there are no loose or exposed wires. Thirdly, the appropriateness of the breaker size. The 70-amp breaker should be appropriately sized for the load that it serves. Perform a load calculation to determine the actual load on the panel and verify that the breaker is sized correctly according to NEC guidelines. Fourthly, the ampacity of the conductors. The number 6 wire must have sufficient ampacity to handle the current that the 70-amp breaker can deliver. Verify that the wire is rated for at least 70 amps, taking into account the termination temperature ratings of the connected equipment and the ambient temperature of the installation. Fifthly, the presence of overcurrent protection. The panel should have overcurrent protection devices, such as circuit breakers or fuses, to protect each circuit from overloads and short circuits. Ensure that all overcurrent protection devices are properly sized and functioning correctly. Sixthly, the grounding and bonding. The panel should be properly grounded and bonded to ensure that any fault current can safely return to the source. Verify that the grounding electrode conductor is properly sized and connected, and that all metal parts of the panel are bonded together. Seventhly, compliance with the NEC. The panel installation should comply with all applicable requirements of the NEC. This includes requirements for wiring methods, overcurrent protection, grounding, and bonding. Eighthly, the presence of arc fault circuit interrupters and ground fault circuit interrupters. Consider installing a size to protect against arc faults, which can cause electrical fires. Also, consider installing GFCIs in areas where there is a risk of water exposure, such as bathrooms, kitchens, and outdoor outlets. Ninthly, the age of the panel. Older panels may not meet current safety standards and may be more likely to have problems. If the panel is very old, consider replacing it with a new one that meets current codes. Tenthly, the history of the panel. If the panel has a history of problems, such as frequent tripping of breakers or evidence of overheating, it may be a sign of a more serious underlying issue. Have the panel inspected by a qualified electrician to determine the cause of the problems and recommend the necessary repairs or upgrades. Here's a discussion of common misconceptions related to electrical panel wiring and breaker sizing. Firstly, thicker wires always mean safer circuits. While it's true that thicker wires generally have a higher ampacity, simply using thicker wires than necessary does not automatically make a circuit safer. The wire size must be matched to the breaker size and the load it will carry. Oversizing wires without adjusting the breaker can create a false sense of security and may not provide adequate protection against overloads. Secondly, the breaker protects the appliance. Circuit breakers are designed to protect the wiring in the circuit, not the appliance itself. If an appliance malfunctions and draws excessive current, the breaker will trip to prevent the wiring from overheating and potentially causing a fire. However, the breaker may not prevent damage to the appliance. Thirdly, it's okay to replace a breaker with a higher amperage one if it keeps tripping. Replacing a breaker with a higher amperage one because the original breaker keeps tripping is extremely dangerous. This is a sign that the circuit is overloaded or that there is a fault in the wiring. Increasing the breaker size will allow more current to flow through the wiring, which can cause it to overheat and potentially start a fire. The underlying problem needs to be addressed, not masked by a larger breaker. Fourthly, all number 12 wire can handle 20 amps. The ampacity of a wire depends on several factors, including its gauge, insulation type, and installation method. While number 12 copper wire with certain insulation types can handle 20 amps under specific conditions, it's not a universal rule. The NEC provides tables and guidelines for determining the allowable ampacity of conductors based on these factors. Fifthly, aluminum wiring is always bad. Aluminum wiring has gotten a bad reputation due to some issues with older installations, particularly with connections that were not properly made or maintained. However, aluminum wiring is still used in some applications, especially for larger gauge wires. When properly installed and maintained with compatible connectors, aluminum wiring can be safe and reliable. Sixthly, more circuits are always better. While it's true that having more circuits can help distribute the load more evenly and prevent overloading individual circuits, simply adding more circuits without considering the overall capacity of the electrical panel can be problematic. The panel must have enough available spaces for the new breakers, and the service entrance conductors must be sized to handle the increased load. Seventhly, a ground fault circuit interrupter, or GFCI, outlet protects the entire circuit. A GFCI outlet only protects the outlets that are wired downstream from it on the same circuit. It does not protect the entire circuit. If you want to protect all the outlets on a circuit with a GFCI, you can install a GFCI breaker in the electrical panel. Eighthly, surge protectors are unnecessary if you have a good grounding system. While a good grounding system is essential for electrical safety, it does not protect against power surges. Surge protectors are designed to absorb or divert excess voltage from surges, which can damage electronic equipment. Ninthly, DIY electrical work is always cheaper. While doing electrical work yourself may seem like a way to save money, it can actually end up costing more in the long run if you make mistakes or violate electrical codes. Incorrect wiring or improper breaker sizing can create serious safety hazards and may require costly repairs by a qualified electrician. Tenthly, electrical panels last forever. Electrical panels have a limited lifespan and should be inspected periodically by a qualified electrician. Over time, components can wear out, connections can loosen, and the panel may no longer meet current safety standards. If the panel is very old or has a history of problems, it may be time to replace it. Always consult a qualified electrician for any electrical work to ensure safety and compliance with electrical codes.